Okay, so hello and welcome to this video tutorial for A-level mechanics. So we have this problem from the June 2023 paper here. I find it quite an interesting problem. Let's just kind of get stuck in here. The problem is about the projection of a ball. It says a small ball is projected with a speed of 28 meters per second from a point O on horizontal ground. After moving for capital T seconds, the ball passes through point A, and we're given these two dimensions here of 40 meters and 20 meters between point O and point A. The motion of the ball is modeled under gravity. Okay. So the first thing that we're being asked to show here is this idea here, that capital T, which is the time it takes for the ball to travel from point O to point A, can be taken as 10 over 7 cos alpha, where alpha is the angle between the kind of initial velocity vector here and the horizontal. First thing to consider, at least in my view, is the horizontal and vertical components of this 28 meters per second velocity vector here. So let's just go ahead and diagrammatize that. So it might look something like this, where we've got 28 meters per second on our diagonal here. We have an angle of alpha with the horizontal. Using a kind of vector decomposition shortcut that I'm trusting you guys are familiar with, we can say that the horizontal component here is 28 cos alpha, and the vertical component here is 28 sine alpha. Just place that. 28 sine alpha. Okay. So this provides us with a useful kind of framework. To answer this first problem here, we want to consider the horizontal motion of the ball, and you can kind of tell that because you've got a cos alpha in the thing we're looking for here. So, okay, we're trying to model, we're only considering the kind of horizontal motion of the ball here. Okay, well, we note that it's traveling at 28 cos alpha meters per second to the right. There's nothing decelerating it because we can kind of neglect air resistance here. To model the motion of this ball, we could make use of these Suvat equations. So our initial velocity, which is also our final velocity, I guess, is equal to 28 cos alpha. Our acceleration is nothing. Our time is what we're looking for here, so let's call it capital T. What else? Displacement, it displaces 40 meters to the right, so S here is going to be 40. Suvat. Okay, cool. We've got all our ideas down. Let's pick an idea out of these Suvat equations here. We want time in there. We want either U or V in there. And I'm assuming we want S in there as well. Let's go with this idea down here. Okay, S equals a half U plus V times T. So we could say that 40 here is equal to a half times U plus V. Note that U and V are the same thing, so I guess we could just write out 28 cos alpha here. 28 cos alpha times T. T for time. Okay, we can rearrange this for capital T now. We can say that capital T is equal to 40 over 28 cos alpha. And we can simplify that to 10 over 7, as we expected. So 10 over 7 cos alpha. Right, let's just highlight that since it's our answer. Okay, cool. let's move on to part B then. So part B is asking, show that tan squared alpha minus 4 tan alpha plus 3 is equal to 0. So for this section, we want to consider the vertical motion of the ball. We understand that we kind of start from a place of 0, we move up to a maximum height here, and then we move back down to a displacement of 20 meters vertically from the origin. So we could go through the exact same process here. We could say u in this context is equal to 28 sine alpha. So u is equal to 28 sine alpha. Our acceleration, since it's being pulled down by gravity, we could say it's equal to minus 9.8 meters per second squared. What else can we say? We don't know the final velocity here. We know its displacement is equal to 20, and the time taken here, we don't know that, well, the time taken was determined earlier, really, wasn't it? It was 10 over 7 cos alpha, so we can say t is equal to 10 over 7 cos alpha. Cool. Right, well, let's pick a suvat idea here. So we're trying to land on something like tan squared alpha minus 4 tan alpha plus 3. We can't pick anything with v in it, so let's rule that out, and let's rule that out, and let's rule that out. Okay, so by process of elimination, we've got a equation here, since we don't know what v is, so we've excluded all the ideas containing v. So we're going to use this s equals ut plus a half at squared idea here. So filling in that formula, we can say 20 is equal to 28 sine alpha times t, which here is 10 over 7 cos alpha plus a half at squared, which in this case is going to be plus a half times minus 9.8 t squared. So woof, 10 squared over 7 squared cos squared alpha. Okay. Evidently, this needs some simplifying, doesn't it? One thing to quickly note here is that we have this kind of sine alpha over cos alpha idea going on here. In case you weren't aware, sine of a thing over cos of a thing is always equivalent to the tan of a thing. So here we can simplify this down to 40 tan alpha, right? So 40 tan alpha. This is still equal to 20. And here we have this is minus 4.9. When I multiply 100 by minus 4.9, that gives 490. And then when I divide that by 49, it's going to give 10 sec squared alpha, since our cos squared alpha is in the denominator here. In case you weren't aware, 1 over cos alpha is equivalent to what we call sec alpha. Okay, so we have this form here. We're clearly narrowing in on our tan squared alpha minus 4 tan alpha plus 3 equals 0 idea. But evidently we have the tan alpha, we don't have the tan squared alpha. We want to kind of convert this sec squared alpha into tan squared alpha in a sense. This is where we can make use of one of what are called the Pythagorean identities. So these are all essentially the same idea, except, you know, to get from sine squared theta plus cos squared theta equals 1 to this, we just divide both sides by cos squared alpha, right? Cos squared theta, and we land on tan squared plus 1 equals sec squared theta here. So we can use that. We can substitute tan squared plus 1 in for sec squared alpha here. Let's go ahead and do that. So that's going to be 10 times 1 plus tan squared alpha. Tan squared alpha. Let's write this all out again. Okay, I'm going to divide both sides by 10 here. So I'm gonna say I have 2 equals. I noticed I made a little mistake here. Apologies. So I've neglected the negative symbol here. Let's just put that back in here. Okay. Now it looks like we have everything we need to reach this form here. We can add 1 to both sides. We can subtract 4 tan alpha from both sides, and we can add tan squared alpha to both sides. So we land on tan squared alpha minus 4 tan alpha plus 3 is equal to 0. Okay. Let's move on to part C then. Here we're being asked to determine the greatest possible height in meters of the ball above the ground as the ball moves from O to A. So clearly here we want to consider the vertical motion of the ball. So we can kind of reuse this process that we used in the previous problem. Here we can say that U is equal to 28 sine alpha. We can say that the ball is accelerating downwards at 9.8 meters per second squared. S is what we're looking for. T we don't know. We're not really bothered with. And V, in a sense, is equal to 0, right? Since the ball kind of moves up while decelerating, and it reaches a maximum point here where its velocity is effectively 0, and then it starts accelerating down towards the ground again. Okay. So we have U, we have A, we have V, we're looking for S. Let's have a look at these, see if our ideas that we have here. Well, that's got V in it, that's got V in it. No, sorry, we don't want anything with T in it. That's got T in it, that's got T in it, that's got T in it, that's got T in it. So we clearly want this V squared equals U squared plus 2AS idea. Let's fill in that formula then. We could say V squared is 0. Is equal to 28 squared sine squared alpha minus 19.6, that's 2 times A here, x, which is what we're denoting S with here, I suppose. So evidently we have an issue with this form here. We have 2 unknowns. We have alpha and we have x. Since we have 2 unknowns in one equation, that is not solvable on its own. Might make sense then to determine alpha. How could we determine alpha? Well, conveniently in the previous question, we derived a equation here that just contains alpha in it, and it's evidently a quadratic equation that we could solve for alpha for here. So let's go ahead and do that. I'm going to say, how shall I denote this? I'm going to say tan alpha is equivalent to x in this context. I've used x twice, but who cares? So I'm going to rewrite this using x here. So I can say x squared minus 4x plus 3 is equal to 0. Let's factorize this. So I can say x minus 1, x minus 3 is equal to 0 here. Therefore, x1 equals 1, and x2 equals 3. Note that x is equal to tan alpha here, so I can say therefore alpha 1 is equal to the inverse tan of 1, which is 1. No, it's not. It's 45 degrees. I don't know why I thought that for a moment there. And our second alpha here can be taken as the inverse tan of 3, which, let me just check my notes here. The inverse tan of 3 is 71.56 here, 71.56 degrees. Okay, so we can assume, seemingly by looking at the graph, we know that that's not a 45-degree angle, right? So I'm going to rule out that alpha is 45 degrees here, and we're going to take this 71.56 value. We can then substitute that in for alpha here. So we can say, let's rearrange this as well. Let's say x here is equal to 28 squared sine squared of 71.56 degrees all over 19.6. We've done multiple steps in one there, but I trust you guys are aware of how we've landed here. So when we put this into our calculator here, we garner 36 meters. We could call it 36.0 meters if we really wanted to. Okay, let's move on to part D then. So part D is a kind of conceptual question. It's asking, the model does not include air resistance. State another limitation of the model. It's an interesting question because excluding air resistance is maybe the most important assumption in this model. Two suggestions I would make here for part D, I'd suggest G could vary, something like that. If you weren't aware, acceleration due to gravity decreases the higher altitude you are. If the ball is only projecting 36 meters in the air, it's going to be quite a small effect, but it is an effect nonetheless, so you could assume that. And another one here you could say is that the model is 2D. So you couldn't use it to model a 3D phenomenon. So that's in effect a limitation of the model here. Okay, cool. So these are our solutions to the problem here. If you have any questions or comments about this problem, please feel free to leave them down in the comment section down below. Otherwise, thank you very much for watching.